Can start, please.
Great. Hi, so my name is Daniel, and I'll be presenting our work, Parallel Algebraic Effect Handlers. This is work with Ningning, Dougal, Maclaurin, and Adam Paszke. So we'll start by giving some background about algebraic effects and about a programming language called DEX that inspired a lot of this work. Then I'll talk about the main contribution of our parallel effect handlers, give some examples of how it can be used, and then talk about some of the things that we want to do to sort of take this approach forward. So start out with some background on algebraic effects. So algebraic effects are a flexible and composable framework for defining a control flow abstraction. And so they can do things like adding sort of mutable state into sort of pure functional code, or adding exception handling, or sort of other types of sort of different ways of interpreting a program with these different sort of effects that happen. And so this is a example of a program in sort of a particular version of algebraic effects based on the lambda calculus, where we have this handle expression, which is given this sort of dictionary of functions. For get and set are two of the effects that the handler handles, and then return is essentially what happens when you have no more effects. And so here is a program that essentially does three things in a row. So first, it's going to set some sort of mutable state to the value 21. Then it's going to get the mutable state and store it in a value n, and then it's going to return n plus n. And then here the 0 is like what the initial state should be. And so essentially what this perform set call is going to do is it's going to then reference this handler function, which determines sort of how these actions should be interpreted when they're executed. And so in general, executing an algebraic effect involves capturing the sort of the execution context where that effect was triggered and passing that to the handler, sort of giving the handler control over how the program executes. And so here we have the same program that I showed you before. And then if we do like one step of simplification on this, what we'll do is this first step here is that we're going to be performing a set of the value 21. And so this will get simplified to essentially pull out the handler for the perform set. So that's right here. Call it with 21, and then give it essentially the rest of the program. So this is called like the continuation or the resumption of the program. And you notice that it has the last two lines of the program, sort of the rest of the program that happens after this first effect. And it also wraps it again in this handler. And so this allows sort of this since it pushes the handler inside, now this will allow it to handle the next effect. And sort of proceeding this way, it'll eventually reduce to the answer of the program, which I guess in this case is 42. Yeah, so here's showing one more step where we sort of apply the handler and simplify it down. So algebraic effects are often assumed to occur sequentially. And so often this is the thing that people want. So for example, in the previous example, we really want to first set the value to 21 before we're going to get the value. And really the only way that it makes sense to do it is to do them in the order that they appear in the program. Sort of more generally, the effect handler generally has access to this full continuation K, which is the entire rest of the program after this effect was triggered. And they're sort of allowed to interrupt or modify the computation of any sort of subsequent effects that occur. And so this is sort of enforces some sort of sequencing because of the semantics of how the effect handlers work, where the sort of the first effect is always going to give control of the rest of the program, and so you have to sort of go in order that they're triggered. Just as a note, there's sort of similar restrictions that apply when you're thinking about things in like monads, which would happen in a language like Haskell. So now changing gears a little bit, I'm going to talk about DEX, which is a new array programming language that sort of is under development. And one of the key features of DEX is that it's a language with a safe, efficient, and differentiable typed indexing. So essentially what that means is that there are particular types that store like arrays. And so here is like a length n table whose type is like this n arrow int. And that means that it's a table that contains n values that are all integers. And so you might write a program called like incr for incrementing a table. and it's going to get passed like some argument x, which is a table of size n of ints, and essentially for each item in the table, it's going to index out like the ith element of the table and then add 1. And so the for keyword here is a special keyword index. And what it does is it builds a new table. And so what it's going to do is we sort of iterate over all values from 1 up to n. And then we're going to essentially build a table whose entries are this expression here. And so the entries end up being the same as the entries of the original table, except that they're incremented by 1. And so one of the key features of DEX is that the iterations of the for loop can be executed in parallel because they have no dependencies on each other. This is sort of a pure functional language. And they can essentially be also compiled very efficiently for these parallel accelerators because they all sort of share the same code. And so it's very easy to sort of run these in parallel over multiple threads or sort of on a GPU over like a very large set of indices. So having this be a pure function is a little bit restrictive. So DEX actually includes a set of built-in effects, which allow some limited interactions between loop iterations. So one example of this is like the state effect, which allows loop iterations to update some sort of mutable reference. And this does actually force sequential execution. And so here is like an example of a function that would take the sum of an array of numbers. In this case, it's an array of size n of floats. Where we do this run state, which sort of is the handler for the built-in state effect. We get this reference object, we sort of loop over the array, and we update the reference. And so this is like where we get the reference, and then this sort of colon equals is the syntactic sugar for setting the reference. And so this is going to then execute serially through each of the loop iterations and sort of update this reference as we go. And so this is actually a little bit more than we need for computing sum, because a sum is actually something we could conceptually compute in parallel. And so DEX also includes a parallel Accum effect, which allows you to sort of take advantage of additional parallelism when the program doesn't really need to be executed serially. So here's again this function sum, but rewritten in terms of the Accum effect. The main difference is that instead of explicitly getting and then setting the reference, we do this sort of plus equals, which is just sort of accumulate some value into the reference. And essentially what we can do is then we can, oh, I just got a message that something is, can everybody still see everything? All right, I'll just keep going. Right, so this plus equals essentially updates the reference in place with some new contribution. And so the advantage of writing the program in this way is that the DEX compiler can actually compute this in parallel, and so it can actually run each of these loop iterations simultaneously, and then do some sort of smart reduction across threads in order to combine to get the full sum without necessarily adding them in sort of a left to right order, but instead sort of whichever order is the most computationally efficient. And so the main thing you lose when you're doing this in parallel is that you can no longer use get within the block. The only thing you're allowed to do is this plus equals. So DEX includes a fixed number of built-in effects, but does not have a user extensible effect system. And so there's many interesting effects that are sort of not supported by DEX today. So one of them is exception handling. So DEX has a little bit of this, but it doesn't have a sort of a full-featured exception handling system. There's also sort of parallel random number generation or sort of enumerative search, and these sort of other things that that would be useful sorts of effects to have. But right now, the reason these aren't implemented is because every effect has to be sort of built into the compiler. And it would be really neat if we were able to instead have these be something that users could sort of write in the DEX core language itself. So that brings us to sort of this work, which is trying to sort of combine the benefits of algebraic effects and the sort of parallel effects as seen in DEX. And so sort of the approach that we're taking is to try to generalize algebraic effects to be sort of parallelizable in the same way that effects are parallelizable in DEX. So essentially what we do is in this work, we formalized a parallel effect system that sort of resembles that of DEX. And we call this lambda p. It's an untyped lambda calculus that features parallel effect handlers. And sort of the main idea, which I'll talk about some more in a bit, is this novel traverse clause, which is an additional thing that a handler has to support, which essentially tells you how to parallelize a for loop. And essentially it tells you how to transform a for loop into a different form that can be sort of executed in parallel. And so here is an example of the sum program. Instead of being indexed now, this is written in lambda p, very similar, with just slightly different syntax. And now essentially this effect is now called like perform Accum, where Accum is the name of the user-defined effect. So I'll just briefly touch on some of the syntax. I'll leave most of the details to the paper. The main thing is that we extend the lambda calculus with table values. So this is like a sort of a tuple of some number of values. We also add 4 expressions, which are similar to dex, sort of range over some number and produce a table whose values are essentially the result of evaluating that expression with each of the different numbers. And we also have sort of handle expressions, which are similar to how they would be in sort of other algebraic effects systems. One thing to note is that we do actually have a sort of a state in our handler, where the handler has some argument s that is sort of the current state where the context in which this handler is executing. So the semantics of the language, so we start with sort of the basics. So the application, where if you apply a value to a lambda function, then that just sort of becomes the substitution. Sort of that's fairly standard. We also have a semantics for sort of these table values, where if you sort of apply a table value with an index, you sort of index out that particular value of the table. Then we have a return and perform, which are fairly similar to sort of a standard algebraic effects system. So return is what happens when you have a sort of effectful context, but the computation you're doing is just pure, like it's just a value. And so then what you do is you call the return function. So this is like the handler is allowed to specify like a return, a function that is like how to handle a return. And so that we just call this function with that value, and so it's allowed to do post-processing if it needs to. We also have perform, which is how you simplify an expression that contains like a perform of an operation inside a handler. So this line just essentially means we look for the innermost handler that handles a particular effect. So each handler can handle a sort of a different set of effects. And so we find the innermost handler that actually handles this effect. We sort of pull out the function that it uses to handle that effect and then call that function. And here, this k is the sort of the continuation or resumption that I mentioned before, where it sort of wraps the rest of the computation. So e is sort of the continuation, the context in which this is executing. And we sort of wrap that in a new copy of the handler and sort of allow this function fp to call this with whatever value it needs to, or maybe not call it, whichever sort of it gives control to this function fp of how it should take care of the rest of the program. And now traverse is sort of the novel part of this work, which is, you can see it resembles a bit the perform, but there are a couple of differences, which I'll go into in some more detail. Just to briefly mention, one of the interesting things is that it actually, every handler must handle the traverse. So whereas for here, some of the handlers, like we would look for the innermost handler that handles the effect, for traverse, we actually go through every handler. So every handler must handle a for loop using this traverse rule. So if we just have sort of normal execution, we can do this sort of single step evaluation, where if we have some simplification that applies to an expression, that simplification will also apply sort of inside an evaluation context E, where here E represents sort of a context where this is like the expression that is like the next one that we want to evaluate. And E is allowed to include additional handlers. So this is sort of just an arbitrary point in the program. Then we also have parallel execution for loops, where here we use something called an F. So this is an F is sort of like E here. It's a part of a program, except that the F is not allowed to contain handlers. And so this is how we disambiguate between sort of for loops that occur at the top of the program and for loops that occur sort of within an effect handler. And so what this rule is essentially saying is that if we have a for loop that we're trying to execute, and that for loop is outside of all the handlers, then the way that we execute it is that we sort of independently reduce each of the sort of possible values of this expression, depending on each index I up to n. And then we construct this table that is the results of all of them and substitute that into the rest of the expression. And so, yeah, I'll go back now to the traverse rule and sort of talk about what this is doing and sort of how we can intuitively understand it. So the main purpose of the traverse clause is to sort of handle these for expressions without sacrificing this parallelism. And so what the traverse rule does is it finds the innermost handler here, H, and it pulls out this traverse clause F sub t and calls it with these four arguments, N, S, L, and K. And so N is the length of the for loop, or the length of the array that the for loop is going to generate. S is sort of the current state of the handler. So it's this argument S that is being passed again to the handler. L and K are then sort of fulfill the role of like the continuation, but it's sort of split into two. So L essentially wraps the for expression itself. So here, this is the original for expression. So it's ranging from the variable X and the expression E. And so here we essentially have wrapped the expression E with this original handler and sort of packaged that up in a function that we're then passing to F sub t. And then K is the sort of the rest of the program. So that's this like capital F here. And that represents sort of the program that happens after the end of the loop. And so it's sort of interesting to emphasize that these are sort of separated in our semantics. And the main reason for that is because in many cases actually, the handler will need to do some sort of processing in between the execution of the loop and sort of the execution of everything following it. So again, we're executing these loops in parallel. And so the handler is going to sort of do whatever it needs to do for each of the iterations at the same time, and then maybe have some sort of like partially computed results corresponding to each iteration. And so then the handler sort of gets the ability to then modify these however it needs to and sort of collect the results across these parallel iterations before it then calls the final resumption and finishes the rest of the program. And as I mentioned briefly before, the traverse rule always applies to the innermost handler, and that's because the context F is required to be pure. It cannot contain any handlers, and it sort of pushes this handler inside the for expression and passes a modified state. So looking at that again, here we have this handle here is passed to this S's is now like a table of additional states. And X is like the index. And so when the handler clause FT here, the traverse clause, can essentially take the state that it's passed and sort of split it up into like n different substates, and then each of the iterations in parallel then processes starting with that substate, and then they can be combined at the end. And so then here we've like exchanged the position of the for and the handle, and so now the for is sort of propagating outward. And once the for is outside of all of the handle, then we can apply this final rule, which allows us to execute the for loop in parallel. So now I'm going to talk about some examples of programs that you can implement using this formalism that I've presented. So I'll start with Accum. So this is sort of analogous to the version of Accum in Dex. I won't go through all of the details here, but sort of the main thing to see is that so we're handling this Accum effect by sort of combining. So the state S here is going to be sort of like the running total of everything. And then here, this is like an infix operator that is like how you combine whatever argument you're passed with the state. And then traverse, what traverse does is it essentially first calls the loop itself, but passes sort of an empty state. So it sort of says like compute each iteration in parallel, but with like starting from like the identity element. Like, so if you're doing addition, this would be like 0. Collect all the results, and then do sort of a reduction across all of those results to combine all of these running totals or all these partial totals into sort of into the entire total across all the iterations, and then only then call this final continuation. And then here is, again, this example of like how you might use this program. And so here's just an example of what it would look like to sort of do one step of simplification of this program. So we have, like, suppose we wanted to sum an array 1, 2, 3. So we'd substitute the definition of sum, which does this handle of a for loop. And so then when you apply this traverse rule, we get like a length 3 array. The initial state was 0 because we sort of started with 0. This L here is this wrapped version of the inside of the loop, where we've wrapped the loop with a copy of the handler. And then the continuation here, there isn't really anything else. We just return the result, and so the continuation just returns the value. And here the traverse is this clause that was on the previous slide, which I've sort of omitted to save space. Another thing you can do is sort of weak exception handling. So this is a way to do exceptions without sacrificing parallelism. The main idea is that when you have a loop and one of the loop iterations throws an error, every other loop iteration continues to execute. So the ones before execute, but also the ones after continue to execute. And then they execute until essentially ending the for loop. And then once the loop ends, they sort of the results are combined, and then at that point the rest of the program stops as well. And so this is just an example of how you might use exceptions combined with accumulation in this case, where we sort of throw an exception at iteration 2. And so here, if you look at the results, we've sort of executed loop iterations 0, 1, 3, and 4, even though 2 threw an exception, but we don't execute anything after the loop. And then this is like the implementation of what that would look like. And you can see the paper for some more details on this. Another really interesting example is a pseudorandom number generation. So if we wanted to generate some sort of random numbers, we'd actually often we're okay with sort of generating random numbers in parallel. Often that's actually something that we would want to do to have a program that is sort of more efficient. So here's just an example program that was like sampling some uniform random numbers, both inside a loop and outside. And so one thing you can do in order to enable this is to use a splittable pseudorandom number generation system. And so this is something that DEX uses. It's also used by the framework JAX, if any of you know of it. And what this essentially does is generates different random number streams in each loop iteration. And so we have this concept of a key, which sort of is like represents this stream of random numbers. And so when we have a traverse with a pseudorandom number generator, we essentially split the key into a number of parallel random streams based on the size of the loop, and then in parallel can execute each of those loop iterations with its own independent random stream. And yeah, just to mention, this is an interesting example where we're sort of using this key as the state. And so this table of keys sort of represents the table of states where each iteration uses a different key. One interesting thing to note is that this actually means that there are actually differences of execution between sort of like executing something in a row versus executing it inside a loop. This is sort of different than like a standard programming language, like or an imperative programming language, where like loops just sort of execute the same thing and have the same sort of semantics as straight line code. But in this case, the for expression is really more like an effect. And so these will actually compute different random numbers because they're sort of a handler for the for that generates the random stream in a different way. One more example is sort of an enumerative search with the amb effect, which is sort of similar to the lists monad in Haskell, which essentially enumerates over all possible execution paths. And so here we say like perform amb over this array, which is like just non-deterministically choose either heads or tails and then combine them across. And what this ends up producing is like a list of all of the different sequences of 3 values that you could get by doing sort of 3 coin flips. And so this can be implemented in sort of a similar way. And one thing that is interesting is that the amb expression actually can call the continuation itself inside a new for expression. And so this allows you to actually introduce parallelism into code that looked sequential in sort of the user space, because we allow the handler to sort of do all sorts of things with the control flow, including call it inside an additional parallel loop. And then here's just an example to show that our system is sort of compositional, where you can combine effects in different ways. You can combine, for instance, the Accum effect with the amb effect to find like pairs of numbers that sum up to some number like 13. So we've implemented a version of this as well in Haskell. So in addition to having this as like an extension of the lambda calculus, we have a version that sort of extends Haskell with these like for and traverse constructs. So I won't go into details about this, but basically this is sort of very similar to these versions of the examples for the lambda calculus, but just with sort of additional things to make it work in Haskell. And so we've implemented each of the different examples that I've shown in Haskell. And so if you can use this if you want to see like what the execution of these different effects and how they compose when you run them. So now I'll talk a bit about some of the limitations of our approach and some of the things that we want to do sort of moving forward. So one interesting thing about our framework is that although it models parallel effects, it does not actually support sequential effects within for expressions. And so one thing that it does not support was the state effect that I introduced at the beginning of the talk, because state effect doesn't actually have a reasonable traverse implementation. So there's no way to take like a for loop with a state effect and turn it into a for loop that is pure, where that loop is executed essentially in parallel, because you actually want to introduce dependencies between the loop iterations. And so DEX uses like a type-directed compilation strategy to distinguish between loops that can be parallelized and loops that sort of must be sequential. We don't currently have something like that for the lambda p, but we're sort of interested in exploring ways of doing something similar while maintaining the sort of extensibility of the system. Another sort of weird thing is that when the handler, there's sort of a lot of things that the handler can do. And one of the things it can do is actually like return the continuation as an object, as like a function, without actually calling it. And so this essentially can have the effect of moving these perform calls around and sort of moving them outside of the initial for loop and splitting it into like two different for loops, one which sort of contains the effects before we packaged all the continuations, and one containing like the effects after. And this can introduce these like synchronization points that end up sort of altering the semantics in surprising ways and sort of leading to these somewhat unexpected interactions between different effects. So here's like an example of like a weird handler where we have like the sync point effect, which just returns the continuation, and then like a traverse, which sort of pulls out all of these different continuations and then immediately calls them in a new loop. And so this really doesn't look like it's doing very much. It looks like it's just sort of delaying computation and then calling it again. But this actually ends up changing behavior, where if you have like a program that is like, so this is a program that uses both accumulation and exceptions and also this sort of weird sync point handler. And so here, if we have two copies of like accumulation, but the sync point in the middle, these accumulations will sort of interact with the exception in the sort of weak way that we talked about earlier, where the loop iterations will all execute in parallel, even though one of them throws an exception. But then because the sync point is there, this second accumulation point will actually not execute, because at the sync point, the exception sort of takes hold and interrupts the execution of the rest of the program. So one consequence of this is, actually this is the main reason that we use sort of introduce explicit state into our handlers, because it's actually not really feasible to do sort of the standard encoding where you sort of transform your program into a program that like takes an additional argument instead of having the state be sort of a primitive of the handler. So that's something that is often done for sort of sequential effects. But if you try to do that in our parallel system, it doesn't work as well, because it sort of introduces these weird sync points. And so we hope that maybe we can prevent this sort of situation from arising using some sort of like type system restrictions on the return type. But we haven't really figured out what the right restrictions should be here and how to ensure that the program sort of has the expected behavior. Yeah, so in conclusion, so we presented untyped lambda calculus lambda p for parallel effect handlers, where we have these four expressions that are handled by a special traverse clause and then eventually can be executed in parallel. There's a variety of interesting examples that can be implemented, but there's some questions that remain, specifically regarding sequential effects, higher order functions, and sort of interactions between handlers. And we're hoping to investigate typed formalism of this language that is able to express like sequential as well as parallel effects in such a way that we could then use this to extend DEX, so allow us to do some sort of effectfully user extensible effect system in DEX based on this kind of framework. Thank you very much, and I'd be happy to take any questions that you have.
Thank you, Daniel. Now we're going to have an interesting discussion, which was partially handled in the chat in parallel to the talk. We have a couple of questions, and some of them are already answered. So we will wait shortly for Ningning to appear on the stage and begin to answer the question. And maybe Daniel can. Oh, yeah. Your treatment of traversal looks very similar to work on scoped effects. Have you compared your approach with work on scoped effects? The question I wanted to ask also.
Yeah, that's interesting. I think I have probably the same answer as Ningning. So I'm not super familiar with scoped effects, and so I haven't looked at what the comparison is. But there's probably some sort of relationship.
Aha! If a sequential calculus can simulate the parallel calculus, do you conjecture discerning properties that the image of the simulation have that the full simulating calculus does not? And this question was already answered by Ningning in the chat. Let's see. Yes. I think the answer is yes. The reverse clause gives user-defined behavior of 4 expressions, but it is totally possible to simulate the semantics with sequential evaluation, and that's essentially what our Haskell implementation is doing. Daniel, do you have something to add?
Yeah, I'm not 100% sure that I understand the question. Oh, Ningning
Yeah.
maybe she can
Nice.
take this question.
Hi. I think Ohada's original question is, can we simulate the calculus with a sequential calculus which just implements the 4 expression like sequentially? I think it's totally possible because like what we do in our calculus is we propagate the 4 expression to the top level, and then we can apply a parallel semantics to the 4 expression. But we can also just simply simulate the sequential semantics of the 4 expression, and I think that is what our Haskell implementation has been doing. Yeah, because we don't really have 4 expressions in the Haskell implementation. And for the follow-up question, I'm not sure I totally get this question. I guess we will need to conduct more study to say something for sure about the sequential semantics of the calculus. So let's leave the question to offline, I guess.
I guess one thing to add is that so it's true that I think it's true that we can simulate the semantics with sort of a non-parallel calculus, but the ultimate goal of what we're trying to do is do this as like a source-to-source compilation that would then run in parallel on like a GPU, and so sort of the reason of we eventually want to actually have this be something that executes in parallel on hardware. And so sort of even though you can simulate it sequentially, sort of we're hoping to actually be able to execute it in parallel without having to reduce to any particular sequential semantics.
Thank you very much. Oh, yes, and one question was answered in chat by Ningning, and we have the last question. Are there alternative abstractions to specify the interaction between parallelism and other effects without requiring each effect handler to implement traverse? Daniel, Ningning, you are muted.
I'm not sure what the other effects mean in this question. I guess it's probably related to like the interaction between parallelism and maybe other sequential effects. But this is really like something we haven't really figured out. I think this is also what Daniel has in the slides. Like currently, we are not sure how to deal with effects that cannot be parallel. And that's true that in our current system, every handler needs to implement traverse, so we can keep handling the full expression until we encounter a pure evaluation context, and then we can evaluate pure full expression in parallel.
Yeah, I think there are some effects where we might be able to have like a default implementation of traverse. I think we mentioned this briefly in the paper, where you can just like have the traverse sort of not do anything and just sort of pass just sort of call the loop and then call the continuation with the results of the loop. That might work for some subset of effects, but then there's other effects where you do sort of need to, where there are actually sort of non-trivial interactions that sort of prevent you from executing in parallel naively. And so those are some of the situations where we're still not sure what the right thing to do is.
Okay. So I see something in the chat. Yes. Meme says that he is fully satisfied with the answer, and that was something he meant in the question. Yes, nice. So we have no questions left, and let's thank the speakers for a very insightful